Good afternoon, this is Schweitzer, and we're going to start our very first video in chemistry here, just kind of looking at, different types of chemistry, and, if you were a chemist in this area, what might you do? Just a quick little start to chemistry here. So, first of all, let's just jump around here a little bit. So, okay, well, in organic chemistry, this person tends to deal with really the chemistry of carbon. And you might say, okay, well, that's it. Well, chemistry of carbon could be someone who deals with generation or development of plastics, maybe making new polymers, making things involving like tires or plastic wrap or this. Someone here might also work with making some sort of like there's a new flat panels called organic layer chemicals like that. So maybe something like that where you're making layers of chemicals involving some sort of technology. Okay, so this type of person can do lots of stuff in the area of technology of modern materials. Inorganic chemists. This one might be a little bit harder to describe. So they're basically dealing with technology, but not involving carbon. So a good example here. So this is non-carbon chemistry, and so lots of times, again, we're in research and development. Both of these guys would be involved in developing new products. So you might think of this person might be specialized in the area of, let's say, batteries. Okay, and they could work in that area. They would specialize in that sort of thing. Okay, so an analytical chemist would be one that would really tell you how much something is present. Okay, so in this case, they might tell you how much lead is in water, for example. Or they might tell you what is present in something, like what is there. Alright, so what is present inside of a sample? Maybe if you were testing for drugs, you would use an analytical chemist. Maybe you're testing professional athletes. Let's say a biochemistry. Now, this is a little different than an organic chemistry. This is literally would be someone who would be looking at chemistry of your actual processes, of organic processes. This might be someone who could be developing, let's say, cancer drugs. Or someone who could be developing a vaccine for some sort of virus. They would be like that. You might even have a branch off of the biochemistry, which would be called a molecular biologist. And that would be even more specialized. And again, that's moving more and more towards biology, a molecular biologist or chemist. And they're really getting into stuff like this more often than not. And obviously, food's everywhere. Whether you're shaping the food to look a certain way. And I'm not talking about, just cutting things in squares. I'm about getting stuff in jars, making it look good, and possibly preserving it so it doesn't rot, or maybe transporting it. Maybe even involve processing it so you can eat it. What's it going to taste like? So lots and lots of stuff. So, take a moment here and think, if you had to be a chemist, or if you're, or maybe, could you see yourself doing something like all these things? So, chemists do lots of things all over our particular spectrum of life. So, all right. So, we have a little chemical demonstration we're going to do here. The chemical demonstration is that of acetylene, and what we do here is you should, if you haven't seen it, you could probably YouTube it. But we have a little Erlenmeyer flask, which looks like this, and we're going to put in some calcium carbide, which is calcium carbide, in this case, add some water, and a chemical reaction occurs, producing what's called acetylene, C2H2. So, what is the name of the substance that explodes? Acetylene. So it's acetylene. Let me spell that one wrong. Now that's the common name as acetylene, like you use an acetylene torch, acetylene welding. Okay. In this situation, we have what's the form of the substance? What's the structure? Let's do this. So it's a carbon with a triple bond like this, and then we could draw it like this. And top and bottom make no difference. You could leave it like this. An organic chemist might just leave it like this. But this is insinuating that there are hydrogens here. So in this case, it is C2H2. And that would be the formula, C2H2. So this literally is just like a building list. Like you could get a list of 2x4s, and you could build stuff out. You could build a tree house, or you could build an actual house. So lots of things happen here. So this is what we call a common name. The chemical name is actually ethine, and we'll see a little bit more about that as we go. This, again, is the common name. Sometimes common. Sometimes things have just historically been around for so long, they just take on a name like water or aspirin. This is obviously very easy to make, and this has been around, and then from that point they can just add oxygen and you can produce, you know, all sorts of good stuff here, which is carbon dioxide and water. Okay. Either way, hopefully you can see that. Alright, so again, structure versus formula. The structure, both these guys have the same formula, which is C4H10. This guy looks like this, and it'd be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And we have here 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. But they're two different chemicals because they have two different structures, even though they have the same formula. So one, structure and formula don't have to be the same. Alright, let's move. So, all chemicals have a name, formula, and structure. That's one thing we kind of want to get through here in this area. So, as we do that, we're going to kind of look a little closer at carbon. So, let's go back to biology. How many times can carbon bond? And it can bond 4 times. Hydrogen can bond 1 time. So, what would a chemical look like if it only had 1 carbon? And hydrogens, and a maximum amount of hydrogens, or we call it saturated with hydrogens. And take a moment to sketch it out. Pause the video. Okay, so 1 carbon, and we have 1, 2, 3, 4. Remember, organic chemists will occasionally leave it just like that. This formula would be CH4. There we go. And it has a name which is called methane. Now, methane is a part of another thing. Common name for this thing might be natural gas. Natural gas is actually a component of this and ethane, but this is a big component of it. One of the most common substances present, and it is actually present in flatulence or gas that will actually start on fire. You could light a fire. Okay. Now, what if we link multiple carbons together? What would it look like? Okay. So what we're going to do here is we're going to take multiple carbons here, add them together, and your job is to add the hydrogens and write the name and then write the formula. Okay. Now we're just starting to get into our naming process on the end here. So add the hydrogens first, and then then you can do the formula, and I'll show you the name because we're just starting to get into that. So pause the video, give it a try. All right. So hydrogens are going to be 1, 2, 3. That's 4 bonds for that carbon, so it's full. So draw hydrogens. 1, 2, 3. So this is going to be C3H6. And that would be the actual formula, not the name. So we'll just back this up here. And this is called ethane. Now again, I got them backwards here, but the name has to produce a formula. Like the name has to be unique to produce that guy. So we're just trying to get into these names. And so there's some stuff going on here. And this is one of our first looks at we call nomenclature. Now, in this nomenclature, I mean, people have nomenclature. Right? It's the process of giving names, okay? It's the process for giving a name. people have this, right? People have a first name, they have a middle name, and they have a last name. And of course, typically in our culture, we, as families combine, we have little means by which we give names out, you know. Same thing for chemicals. Nomenclature is how do we give this name to that chemical? How could I cover this up, okay, if given this name, how would I produce that? Alright, so that's where we're leading. Okay, now again, the rest of these guys, you should pause the video and have your hydrogens added, if not already. Alright, 1, 2, 3, 4, 5, 6, 7, 8. I like to count them as I go. C3H8 is the formula, and this is called propane. Kind of similar. And we just had methane in the last slide. Okay. This guy is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's 10 hydrogens. C4H10. And this guy is going to be butane. Okay. So we're seeing some commonalities amongst these guys and some differences. So eventually we're going to move toward how we can figure out how these names are working. Alright, so now butane. What's going on here? Okay, well, it turns out that the first part of this name is the number of carbons. Okay, it used to be the total number of carbons. That's a long time ago. They've now changed it to the number of carbons in the longest chain. The longest continuous chain. Doesn't matter if it's bent or straight. This is a continuous chain. The longest continuous chain. Alright, so, and then the end here, this ane means single bonds. Only single bonds. Okay, and we'll see that change as we move along here. And when you only have single bonds, that means you have maximum number of hydrogens, and there's a term we use for that called saturated. And you might hear like saturated fat, and that's really what it is. So these carbons here, these prefixes, let's just do this quickly here. It's mono, hold on a second here, it would be methyl. Now I'm drawing in this YL, that's commonly dropped at times. So like methane, they drop the YL, ethyl, propyl, butyl. Now, organic chemistry's been around for a while, so these first four were just purely adopted on historical. And there's a little story behind each one of these names at some point. But otherwise, in the rest of chemistry, we use the Latin form, which is mono, di, tri, and tetra. And only in this little brief organic section do we use these guys. Otherwise, we use entirely this guy right there. That's only for the means of telling us the number of carbons. Okay. Either way, the rest of the time we flip to the normal Latin form, which is penta, hexa, hepta, octa, nona, and deca. Okay, so hexane. Let's draw a structure of this thing. What does hex mean? Hex means the longest continuous chain, 6 carbons. Now again, you should note that these little guys are like little strings, and this thing really turns and flops. These carbons spin. This thing is like a piece of spaghetti. Okay, literally, if you were to take a bunch of long things like this and then dry them out, like get rid of the solvent so they couldn't move around, this is what you call like a varnish on top of wood. It literally is just a big layer of spaghetti. It dries, and the layers get caught up in each other, and they stick and form a little layer. That's how clear varnishes and lots of things that cover our coatings on materials work. Paint, for example. So hex means 6 carbons. So 1, I'm going to draw them straight here, but in reality they're not straight. 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay. Ene means only a single bond, so it's maximum hydrogens. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. 14 carbons long. That's C6H14. Alright, take a moment, add your carbons, and pause the video, write the formula out, the name and the formula. Pause the video. Alright, so we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So 1, 2, 3, 4, 5, 6, 7, 8. That's C8H18, and this is going to be called octane. Okay. Alright, so there we go. We got a couple of practice ones here, and that's pretty much a good chunk of what we're looking for here. We'll be adding some bells and whistles around the outside of these things, and the inside we call functional groups. But that's going to be coming up here momentarily. Okay, so let's pause here for a moment and pause the video and see how many different ways can you rearrange these particular 5 carbons. Okay, pause the video. If you had 5 carbons, could you rearrange and make more than one substance? Alright, so pause it, try it. Alright, so what do you got here? So obviously you got 1, 2, 3, 4, 5. Okay, and then what else could we do here? Lots of times we'll do different things. They might say 1, 2, 3, 4, 5, but that's not it. That's the same thing. That's no difference. Or you could do something different, like let's say 1, 2, 3, 4, 5. That's the same as that if they flipped it around. So that's out. What else we got here? We could do 1, 2, 3, 4, 5. Now that's different. Okay, our longest continuous chain here is only 4 carbons. So this name would be pentane, but this one would not be pentane because it's only got 4 carbons. It would start with a bute, and it would be a little bit different name. We would have to tell them the longest continuous chain is 4 carbons, and then we have another guy hanging off here on the second carbon. So we'll get to that momentarily here. There's one more left. Hopefully you could try it. It is 1, 2, 3, 4, and 5. Now this longest continuous chain is only 3. So this would start with propane, and this is butane because it's all single bonds. But we need something else on here to tell it that there's now two groups hanging on here. Okay, so kind of interesting. All right, and 4-methylhexane. Okay, we're going to pause this video here, and with our basic number naming system here, we'll get to be our time long enough, and just looked at basic shapes as far as how long they are, giving some basic names to how long is chains. And next video will add on some functional groups and a little more complicated names. Thank you.